In this unit, we are going to be studying gases. So to start off the unit, let's talk about some characteristics of gases. The first is that gases have very different chemical properties, and we've already seen this when we looked at chemical reactions, that the way that they react is very different. However, they have very similar physical properties. So let's look at some of those physical properties right now. Gases expand spontaneously when they're put into a container. So while liquids assume the shape of their container, gases not only assume the shape of the container, but they also assume the volume of the container. They completely fill that container. Another characteristic of gases is the fact that they are compressible. Now, gases tend to take up only about 0.1% of the total volume of the container that they're in. And as a result, they can be compressed very easily because most of the volume that they take up is actually just air. Now, other states of matter, solids and liquids, are not compressible, and you will have experienced that if you've ever fallen onto the ground or if you've ever belly flopped into a swimming pool. Those states of matter do not compress while air or gases do. When two or more gases come together, they actually form a homogeneous mixture. So unlike liquids or solids, which when they're mixed together can either form heterogeneous or homogeneous mixtures, gases will always form homogeneous mixtures. The interesting thing, though, is that when they form mixtures, gases don't actually interact with one another. They actually act independently of one another, and that will be important when we start to study Dalton's law of partial pressures. The next concept related to gases that we need to talk about is pressure. So the official definition of pressure is that it's a force acting on a specific amount of area. Before we actually get started with pressure, there is one question I want to ask you, and it's that if gas molecules experience gravity, which they do, are they pulled towards the earth like a falling object? So if I drop a baseball, is that how gas molecules experience gravity? And the answer to that is no, that gas molecules, since they have such small masses, their kinetic energy actually prevents them from falling to the earth. But we do still experience gas molecules, and we experience them because they do actually press down on the Earth's surface, and that pressing down, that force over the surface area of the Earth, that is what we call atmospheric pressure. So gas molecules still experience gravity, and the way that we experience their experience of gravity is atmospheric pressure. Now, that actually makes a lot of sense, because if we climb up a mountain, when we're at the top of the mountain, we experience a very low atmospheric pressure. And the reason why is because there's actually less atmosphere, there's less gas that is pushing down on us. If we go below sea level, then we experience more atmospheric pressure. And the reason why is because there's actually more atmosphere that is pushing down on us. So the official definition of atmospheric pressure is that it's the force exerted by the atmosphere over a given surface area. As with all concepts that we've looked at in chemistry, we have to be able to quantitatively describe pressure. And the first person to provide us with a tool to be able to describe quantitatively pressure was Torricelli. And Torricelli came up with the tool that's called a barometer. So if you look at this diagram right here, what you have is a bath that is filled with mercury, and then a tube, a closed tube, that is also filled with mercury. So that mercury tube is actually inverted into the mercury bath. What atmospheric pressure does is it provides a force onto the bath of mercury, causing the mercury that's in the tube either to rise in the tube or lower in the tube. Now, the height, the lowercase h that you see right there, that is actually a measure of how large the atmospheric pressure is. So the larger your lowercase h, the larger your atmospheric pressure. And so standard atmospheric pressure, what we consider to be standard, is 760 millimeters of mercury. So when that column has 760 millimeters of mercury in it, that's what we call standard atmospheric pressure. Now there are of course other units for measuring pressure, and those include atmospheres. So 1 atmosphere equals 760 millimeters of mercury. Torr, pascals, and kilopascals. Another tool that we can use in the laboratory in order to measure the pressure that gases exert, not necessarily atmospheric pressure, but that gases exert, is a manometer. Now there are two different types of manometers. There's a closed-end manometer and an open-end manometer. So in a closed-end manometer, it's not experiencing atmospheric pressure because it's closed off. So as a result, if you look at this manometer here, the mercury, which is in gray, originally it started off at the same level on the left-hand side and the right-hand side. But once the gas that is in purple is able to exert a pressure onto the mercury, it causes the mercury on the right-hand side to rise higher than the mercury on the left-hand side. The height difference between the two mercuries, that represents the pressure that the gas exerts. So for example, if I ask you what is the pressure of a gas if the lowercase h, the height of the mercury, is 10.3 centimeters, you just have to convert that into millimeters of mercury, and that will be the pressure that the gas exerts. So if I'm given 10.3 centimeters, I need to put centimeters on bottom, and there's 1 centimeter, millimeters up top, and there are 10 millimeters in 1 centimeter. So the total pressure that that gas exerts is 103 millimeters of mercury. In an open-end manometer, atmospheric pressure does play a role. So let's look at the first one on the left-hand side. So if you notice, this is an open-end manometer, so the atmospheric pressure is pushing the mercury down on the right-hand side, while the gas, the purple gas, is exerting a force on the left-hand side. And so the difference between those two, we need to use the H. That represents the difference between the pressure that the atmosphere exerts and that the gas exerts. If you look on the left-hand side one, since the mercury is higher on the left-hand side, that tells us that the atmospheric pressure is actually larger than the gas's pressure. And so as a result, we can say that the atmospheric pressure equals the pressure of the gas and the height that that mercury has risen. So for example, if you look at this example problem, it says that the atmospheric pressure is 755 millimeters of mercury, and that level, the level of the mercury, is 75 millimeters. So I know that the 755 millimeters of mercury, which is the atmospheric pressure, I need to subtract from that the height that that mercury has traveled, because I know that the pressure of the gas is that much less than the pressure of the atmosphere. So I'm going to take 755 millimeters of mercury, and I'm going to subtract from that 75 millimeters of mercury. That will tell me the pressure of my gas, which is 680 millimeters of mercury. In contrast, if the mercury has risen on the right-hand side like it has in C, what that tells me is that the pressure of my gas is that much more than the atmospheric pressure. So the pressure of my gas equals the atmospheric pressure plus that pressure, which can be measured by how much the mercury has risen. So in this example, I start with 755 millimeters of mercury plus however high the mercury has risen, which is 75 millimeters of mercury, and that will be the pressure of my gas. And therefore I get 830 millimeters of mercury. So notice the only difference between open-end and closed-end manometers is the fact that in closed-end manometers, atmospheric pressure plays no role, while in open-end manometers, you have to consider the role that atmospheric pressure plays, specifically whether or not the atmospheric pressure is higher or lower than the pressure that the gas exerts. If it's higher, then the mercury will have risen on the left-hand side. If it is less, then the mercury will have risen on the right-hand side of that manometer. And then you can complete the math that's necessary in order to calculate the pressure of the gas. Now that we've talked about pressure and measuring pressure, let's actually talk about the units and unit conversion that's required. So if I give you a problem like this one, in which I have 1,277 millimeters of mercury, and I ask you to convert to atmospheres, what you need to do is you need to put the units millimeters of mercury on bottom, which is 760 millimeters of mercury, and the units atmospheres up top. And remember, it's 1 atmosphere. So this conversion factor that was given to you on the previous page, in which I told you 1 atmosphere equals 760 millimeters of mercury. Now all you have to do is divide and make sure you only have 4 sig figs. So that's your final answer. We're now going to talk briefly about 5 different laws which you should have been introduced to in your first year of chemistry. The first one is Boyle's law. And what Boyle realized was that if he added more pressure to a manometer, then the volume of a gas would decrease. So if you look at the diagrams to the left-hand side, it's experiencing 760 torr, or 760 millimeters of mercury, and the volume of the gas is 60 milliliters. Now, if I double the atmospheric pressure, so I add another 760 millimeters of mercury by literally adding mercury, then the volume of the gas decreases to 30. So when I doubled pressure, he realized that the volume halved. So here's the relationship he discovered. He discovered that the volume of a fixed quantity of gas maintained at constant temperature, and that's key, that temperature is not changing, it is inversely proportional to the pressure. So when I double pressure, volume halves. This relationship here, that the volume equals constant times 1 over P, that represents that inverse relationship. This is a graphical representation of what he discovered. If you look at the graph on the left-hand side, what that's showing you is that as pressure increases on the x-axis, volume decreases, and you can see that curve there. Now, if I want a linear representation, what I need to do is I need to either put volume or pressure in the denominator. So in this example on the right-hand side in the graph, it's 1 over P. Now, that will create a linear graph because that demonstrates the inverse relationship between volume and pressure. And finally, what this law enables us to do is if we know the pressure and volume of a gas, if we change that pressure, it enables us to predict what the new volume will be. So it's P1 times V1 equals P2 times V2. So in a problem, you would be given 3 of these variables and asked to solve for the 4th one. The next law is Charles' law, and as you can see right here, what Charles' law tells you is that volume and temperature, since there's a linear relationship, they're directly related to one another. Notice with this dotted line, these are extrapolated values. Specifically, if you notice, the temperature is extremely low here, and the reason why these haven't been able to be measured is because at such a low temperature, these gases actually become liquids and solids, so it's not actually feasible to measure the volume of these molecules because they are no longer gases. But what Charles did note was that the volume of a fixed amount of gas, if it's kept at a constant pressure, which is key, it is directly proportional to its absolute temperature. By absolute temperature, it means Kelvin. Okay, so all of the calculations we'll do with Charles' law, those need to be in Kelvin. Notice here that volume equals a constant times T, that represents a direct relationship. And here, this allows me to note how volume or temperature will be affected if I change the volume or temperature. So for example, if I start with a volume and temperature for a gas, and I increase the temperature, I can actually predict what the new volume will be. The next law is Gay-Lussac's law. So Gay-Lussac's law noted that the pressure of a fixed volume of gas increases as the temperature of the gas increases. So note, pressure is directly related to temperature, all right, which is represented here, but I have to keep the volume constant. And so here's your quantitative way of determining what happens to a gas if I change either pressure or temperature. Now, if I take all of these laws and combine them together, I get the combined gas law, which is P1 times V1 all over T1 equals P2 times V2 over T2. So if I'm given 5 of these variables, I can solve for the 6th. So if nothing is being kept constant, if I change my pressure, my volume, and my temperature, I can quantitatively determine what happens to that last variable, whether it increases or decreases, and the specific quantity. The last law that we're going to talk about is Avogadro's law. Now, Avogadro's hypothesis stated that equal volumes of gases at the same temperature and pressure will contain equal numbers of molecules. So you can actually see that right here. Helium, nitrogen, and methane all have the same volume. They're experiencing the same pressure and temperature. And even though they have different masses, you still have the same number of molecules because these are not tightly packed in. Instead, remember that gases are extremely far apart from one another, and therefore when we're talking about gases, if they're occupying the same volume and they have the same pressure and temperature, you're going to have the same number of molecules. So Avogadro's law states that the volume of a gas, if it's maintained at constant temperature and pressure, it is directly proportional to the number of moles of the gas. So if I increase the volume, then the number of moles, the number of molecules of that gas will increase as well. And so that's represented here, where the volume equals a constant times N, which is your number of moles.